Hey, welcome back to Mama Physics. In this video, we're going to continue doing vertical circle examples. So this is 6.1 part 2. And we're going to look at banked curves, okay? Banked curves, meaning most of the time you've been dealing with either objects moving around in a horizontal plane, or you've been dealing with objects moving around in the vertical plane. So a merry-go-round or something like that. Banked curves, imagine that your object is moving around in a circle in which the path that they follow is at an angle, okay? So, for example, if you might remember either yourself driving onto the highway or driving on a highway, or if you are sitting in a car and your parents are driving you along the highway, imagine think about times where you had to make a very sharp curve or a very sharp turn on the highway. The highway would, you might notice that the floor is not exactly flat. It might be tilted at an angle. And you kind of have to think about that. Well, it has to be there. Otherwise, if your car's traveling too fast, it might just fly out of the highway, which is not really good. So you might have areas which are banked, which is what this is talking about. Another example, if you think about it, is imagine you're a waiter or a waitress, and you're trying to, you're holding a tray of water, and maybe it's wine glasses, and you have to maneuver around the restaurant really quickly. So imagine you have to turn a really sharp curve, okay? You might notice that if you just held the tray flat, your glasses are going to fly away. But if you kind of tilt it a little bit, you can kind of maneuver yourself a little bit better around the restaurant. So these are the banked curves that allow your object to move in a circle, in which when you do that, you have to apply a force not directly up, not directly horizontal, but at an angle. So the forces that cause your object to move around in the circle are directed at an angle. Okay, so that's the idea of banked curves. We got two here that I'm going to talk about. One of them is a car moving around a banked curve, and let me see if I can pull a picture. But the first thing that comes into mind is Mario Kart. Some of you might play Mario Kart, in which you have a big kind of like a bowl shape. So let's see if I can put a picture of that. So I tried to look at some Google images, and I was able to find a few examples. So I had to Google Mario Kart sharp turns. Stadium didn't really work, didn't give me all the results. And I don't own the game, so I don't remember what the stadiums were called. But I just remember there was one where there's a big bowl, and it was like a PvP game where you kind of shoot each other's balloons or something. But here I just I just have found a few images here. So notice that for these sharp turns, notice that the road becomes slightly tilted at an angle. It almost feels like an incline, which we'll talk about in a second. Here's another example, and notice the top 3 images that came up are all banked curves. So there you go, banked curves for you. Let me see, and there are some other examples, but hopefully you kind of get the idea what a banked curve would look like. And even if you don't play Mario Kart, you might have played other maybe racing games where you have to take a really sharp turn when you're going really fast. You might notice that the road becomes a little bit curved. A little bit banked for that matter. So this is what the example 3 is all about. Calculate the angle at which a frictionless curve must be banked if a car is to round it safely at a speed of 22 meters per second. And if its radius is 475 meters. Okay, so let's draw a diagram. And I probably will need a little bit more space, so I might have to draw all over here as well. Okay, so imagine that I have a banked curve. So a car would be traveling, so let's draw it over here. So imagine this is a stadium, okay, and here's the bank curve. And he's kind of going around this bank curve like this. going really fast, okay? And, well, even if it's not a stadium, imagine if it's just a highway. I'm going to draw from the side view, or actually from the behind view of the car. So I'm going to draw the car from behind, even if the car was traveling forward. So the car would look like this, okay? So its wheels will look like this, and the road needs to be slightly tilted in order for the car, if it's going really fast into the page, then it might slip. But we want to find this angle at which it needs to be banked so it will not slip. So it kind of holds it a little bit in place for that to happen. Okay, so a few numbers to note. Now, when we have a banked curve, usually there is a circle associated with that. So the circle in this case, you have to imagine as this one over here. So not all highways, I mean, for a highway, you don't really go around in circles. But imagine that a road was designed so that it was banked at 6 degrees, and then you kind of just took that and you rotated around in a perfect circle. At a radius of 475 meters, then imagine you take the whole thing and you kind of like spin it around to create the road. If you kind of take that plane and you kind of make that road, that's what it would look like. So imagine the car was always going around in a circle, then this is the radius, 475 meters. It's hard to imagine, I suppose. The next thing, we're going to have to draw a free body diagram on the car, so we know there is gravity acting on this car, and since he is banked, he's on an kind of like an incline. He has a normal force acting on him at a diagonal, and there is no friction here, so we don't have to draw the friction force. We might have to resolve a few vectors, but here is where it is very important. The most important thing about doing these bank curves is determining the axes that you're interested in. Now, because the radius of the circle, 475 meters, it's kind of parallel with the bottom of the ground. So it's a direct horizontal line across the page. So the direction of acceleration, centripetal acceleration, is this way, is towards the center of the circle. So remember when we talked about setting up axes? To set up the axes, we want at least one of the axes to be in the direction of acceleration. Since the acceleration is directly horizontal, we need one of the axes to be a horizontal line. So that's going to look like this. That's going to be our x-axis. Why not? And then our y-axis is going to be this one. And you're like, what? Because normally you would set the axes at an angle because of an incline. But guess what? We're not doing an incline problem. This is not an incline. The car, remember when we talked about inclines are when the object slides down the incline. So the acceleration is down the incline. But for a banked curve question, the car's centripetal acceleration is directed towards the center of the circle, which is along a horizontal line, the horizontal axis of x. So now we have to set the axes differently than before because of this new direction of acceleration. And notice, this car is still going along the banked curve. It's not sliding. Because it's not sliding, there is no acceleration up and down the incline. Which means, when we resolve our vectors, we have to resolve it differently than how we did it before. Okay, so I'm going to redraw this one here on another page to show you what this angle here would be. So this angle, we're going to call that theta. That's the one that we want to find out. So let's just extend some of these lines a little bit. So take a look at this line, which is our x-axis. So if I draw a line that's parallel with my incline, it's going to look like this. Okay, and if I draw a line that kind of continues off with the ground, we know that this angle is theta. And two lines, assuming these are both parallel lines, then we know that this angle here must also be theta. We know that the normal the normal force is perpendicular to the incline, the line that's parallel with the incline. So we know this one here is 90 degrees, okay? So we know this guy here is 90 degrees, meaning that if this angle is theta, this guy over here is the complementary angle to theta, which is 90 minus theta, okay? Now here's another 90-degree angle, which is this one over here, which is the between the x-axis and the y-axis. We know that's also 90 degrees as well. So this is 90 degrees, or I don't know, this one, okay? Now since this whole thing is 90 degrees, if this is 90 minus theta, this is the complementary angle to that, which then is 90 minus theta altogether, which of course is just the complementary. That will be the original theta right there, okay? So let's go back to our original ugly drawing, which I'm gonna erase a lot of. So based off of this diagram that we have, we know that this angle here is theta, okay? So then when we resolve our Fn into its vectors, we are going to have this one over here being Fn times cosine of theta, and this up there, the horizontal component of Fn towards the center of the circle, this is going to be Fn sine theta. Okay, so that's the horizontal vector over there. Okay, so now we have that. And then we're going to look at example 3, which the angle should it be for the car to be able to make it around the circle. To do that, we have to write the F net equation that is pointing towards the center of the circle. So we have F net is equal to, well, let's take a look. Let's take a look at all of our vectors. FG is pointing perpendicular to the center of the circle, which cannot be FG. FG does nothing here. But if you take a look at Fn, one component of the Fn is pointing towards the center of the circle, which is Fnx. So that's Fn sine theta. It's the horizontal component of Fn. So we're going to write here Fn sine theta is responsible for keeping the object moving around in the around the circle. And that's going to be equal to mass times centripetal acceleration, which we know is v squared over r. Okay. Now, we don't know what Fn is. We know what m is. Actually, we don't even know what m is. We know what v is. We know what r is. We can't solve for the theta yet because we don't know what Fn is. But don't forget, we have two axes to work with. One, the horizontal one, in which the acceleration is occurring, and then the vertical one, in which no acceleration is occurring. But in the vertical one, we know that the Fg pointing downwards is going to be equal to the vertical normal force component, which is Fn cosine theta. Okay? So notice that these two vectors are going to be balanced. They must equal to one another. So now we do have a way to find Fn. But I think what we have to do here is we kind of have to solve for Fn and substitute it into our original equation. So to do that, I'm going to divide both sides by cosine theta, and which then is going to leave me with Fn is equal to Fg, which I'm going to write mg for, mg cosine theta, okay? And I'm going to substitute this Fn in there, in my F net equation to begin with. So I'm going to be left with here, mg, okay, divided by cosine theta, which I substituted in here, and right beside it I have sine theta is equal to mv squared over r. Now you might notice that the masses, the m's, can cancel out. So this m cancels out with this one. And I'm going to be left with, okay, let's erase this one. I am going to be left with, okay, this is going to give me g. And, oops, not just g, but I'm going to be left with g sine theta over cosine theta is equal to v squared over r. You might think, well, now I got two thetas. How do I combine them together? To combine these together, which I'm going to do on the next page over here, we know that there's an identity, or there is a relationship between sine theta divided by cosine theta. This is going to give us tan theta. Woohoo, tan theta. So G tan theta is now equal to V squared over R. Now we can solve for theta now, because we've combined the sines and cosines together. We just have to divide this side by G. Okay, that goes away. And to get theta, we're just going to take the inverse tan of a V squared over RG. And that's going to be, let's see what it is. V is the speed. That is 22. And then radius 475. Okay, so 22 is going to be squared. Radius is 475 meters times gravity 9.81. Okay, and after I divide those, I am going to take the inverse tan. Don't forget, you want your calculator to be in degree mode. And I get 5.9299 degrees. How many sig figs do we need in this one? There's about 2 sig figs. 2 sig figs. Okay, so somehow I got 5.9 degrees, not exactly 6. So the banked curve needs to be 5.9 degrees. Let me just double check my calculations. Okay, I get 5.9, so not exactly 6. So maybe some rounding happened when I did the key. But anyways, we should get 5.9, not 6. Okay, 5.9 degrees. Okay, so that was example 3 for banked curve. So this problem can be more complicated depending on if there is friction or not. So if you, let's say if there was friction. And this, of course, if this car is going too fast along this banked curve, then let's take a look at the original equation here. We have this one over here. Okay, so that's the normal force. The normal force, as you can see, can only be so much because it depends on mg. And let's say you have a fixed bank. You can't really change the angle of your bank, which means Fn is fixed. Meaning that if you go too fast, you're going to exceed this the force that is able to keep you moving in the center of the circle. So you're going to fly off, okay? And if you fly off, the only other force that's going to keep you within the circle is the friction force. So imagine your car, imagine there is a friction force now. Because your car is, say, going too fast, think about which direction friction force would be. If your car's going too fast, you're going to start sliding upwards, which means the friction force will be in the opposite direction, going down the incline. And then you got a few other vectors you have to work with, because notice the force of friction going down the incline, the banked curve. A component of it is directed towards the center of the circle. So you get a little bit more force that is able to hold your car in so it doesn't slide away. But if your car goes too slowly, and which, let's say you have an icy path or something like that, you're going to start sliding down. So depending on how fast your car is going, if it's going too fast, if it's going too slow, notice the friction force will try to work against the direction in which the car is going to slide, which will then change up your F-net equation. So the problem will get more complicated with friction. So hopefully this gave you a basis of how to solve these problems. The key thing is to figure out the direction of the centripetal acceleration to align your axes properly. So thank you for watching. Good luck. I'm going to do example 4 next. And Fan Mama Physics signing out for now.